Today we are going to start second order circuits, and in today's lecture we are going to study the basics regarding second order circuits, and we are going to solve some problems so that all your concepts would get clear. What are second order circuits? Second circuit is characterized by second order differential equations. It consists of resistors and equivalent to energy storage elements. In simple words, if the number of energy storage elements increases, then the complexity of our equation also increases, right? So this kind of circuits are called second order circuits, or we may say the circuits which are going to form the second order equations, the equations which we are going to generate from any circuit. If they are of second order, then we'll call them as second order circuits. Now, first of all, to step forward towards second order circuit, we must know what is V of 0, I of 0, I of 0 positive, I of 0 negative, d of V, derivative of V of t, d of I of infinite, and V of infinite. These are all the initial and final conditions, initial and final values which must be understood. You all must know how to find out all these values in any kind of circuit. So to find out these values, you have to memorize, or you have to keep in mind the following few points. As the first one is, you have to know how to handle the polarities of the circuit. These polarities we are studying from your first year. What are the directions, what are the polarities of any component? Capacitor voltage is always continuous. It means that when you have some value of V at 0 positive, then as it is continuous, it would not vary instantly. So the value of V of 0 negative is also the same. Or you may say that when you have value of V of 0 negative, or when you find out the value of 0, V at V of 0 negative, then V of 0 positive would also be same. Similarly, in case of inductor, the current doesn't vary. I of 0 positive is equal to I of 0 negative. It would not vary instantaneously. T is equal to 0 negative is the time before switching event. What is the switching event? This one, if you have this type of symbol in your circuit at T is equal to 0, then it means then when T is not equal to 0, then this arrow is not connected to this line, right? Like this arrow is open, it is not connected to this point. And when the condition is given that at t is equal to 0, this condition was given, and we may say that at t is equal to 0, you have to connect these two components, you have to connect the switch, then this must be connected. Similarly, t of 0 positive is time just after the switching event occurs. If you say that what is t greater than 0 or t positive of 0, it means that after this connection, after this connectivity, after connecting the switch, if switch is open, you have to connect it. And mostly switching event takes place at t is equal to 0 most of the time, but the condition may reverse. Now let's solve a problem. It would clear your concepts further, right? It is your example from your book to develop a clear understanding. The switch and the figure, this figure has been closed for a long time. It is closed for a long time and it is open at t is equal to 0. See, the situation reversed. Situation is opposite as we have discussed previously. Now what we have to find out? We have to find out I of 0 positive, V of 0 positive, T of I over dt of 0 positive, V of 0 V of 0 positive over dt, it means derivative, I of infinite and V of infinite. All the things which we have discussed in our previous slide. Now, first of all, what we are going to do? we have to consider the initial conditions. If the switch is closed for long time before t is equal to 0, it means that the circuit has reached a DC steady state. Remember the steady state which we have studied previously also. At DC steady state, the inductor acts like a short circuit and the capacitor acts like an open circuit. Look, this inductor, it is a short circuit, and this capacitor, it is an open circuit. It is clearly elaborated in figure A, right? So, at t of 0 negative, we got I of 0 negative is equal to 12 over 4 plus 2. This one is 4, this one is 2, this one is 12, which is equal to 2 ampere. How? This is simple KVL, simplest KVL. As we know that now our circuit is in series, so we just combine the values of resistors. They are 4 plus 2, that is 6, and V over R, we got I of 0 negative. When my circuit was in steady state, as we know that the condition is at t is equal to 0, the switch would get open and my circuit, these points of my circuit would got not come in not connected state. So what was the previous state? Previous state, this switch was connected, and in continuous connection of this switch, our circuit is in steady state, and in steady state, my inductor is going to act as short circuit and capacitor is going to act as an open circuit. So this was the condition, and in this condition we have to find out the value of I of 0 negative. I of before time t is equal to 0 means time before t is equal to 0 means time of 0 negative side of the number line, right? And similarly we got V of 0 negative is equal to, what is the V of 0 negative? It is equal to, this one is V. 2, what is 2? 2 is the value of resistor, multiply by I of 0, which we have find out in our previous step, which is equal to 4 volts. Now, as we know, we have studied in our previous slide that the inductor current and capacitor voltage cannot change abruptly. So, immediately at t of 0 positive, it is equal to, at I of 0 positive, it is equal to I of 0 negative, right? Which is equal to this one, same, 2 ampere. Similarly, V of 0 positive, which is equal to V of 0 negative, and it is equal to 4 volts. Now, the part B of our problem. What is the part B? The part B states that you have to find out the value of value at t greater than 0, not t less than 0, not t equal to 0. It would be the value of t value of all the components I, V at t greater than 0. Now, when the switch is given, the time is greater than 0, the switch would be what would be the condition of our switch? It would change its state from normally closed to open one, and after getting that state, the central branch, the branch over here like this, it comes in not connected state, and our circuit look like this. This is the equivalent circuit. Now, the same current flows through both the inductor and the capacitor. So, I of C of 0 positive is equal to I of 0 positive. Why? Because they both come in series state, and that we have already find out in our previous set is 2 amperes. Now, C dV over dt is equal to IC, is equivalent to IC. We have studied this is from our first lecture, I think. And dV over dt is equal to IC over C. This C comes below this IC, right? So, dV over dt of 0 positive, this was one of the things we have to find out in our given question, is equal to IC of 0 positive over C, which is equal to 2 amperes divided by 0.1, which is the value given over here, is equal to 20 volts per second. Similarly, L di over dt is equal to VL. So di over dt is equal to VL over L, and as we already have calculated V of L, no, sorry, we haven't calculated V of L, we have calculated I of L, remember in previous step. So we have to find out the value of V of L by using the Kirchhoff's voltage law, right? So apply Kirchhoff's voltage law on this circuit number B. So minus 12 volt plus 4 into I of 0 positive plus VL of 0 positive. Why? This one inductor, we have to find out the value of this voltage drop across inductor, plus V of 0 positive. This one was the voltage drop across capacitor, and this one was the one thing which we have calculated in our part A of this question. Now, rearranging our equation, taking this on this side of is equal to and remaining part on the other side, what we find out? We find out that 12 minus 8 minus 4 is equal to 0. So VL of 0 positive is equal to what? 0. Now di of 0 positive over dt is equal to VL of 0 over L. So 0 over any value of L is equal to 0 again. So another value we have calculated from these steps. Now last one, for t greater than 0. What we have find out? T less than 0, t is equal to 0. Now the third thing is, what would be the values at t greater than 0? The t approaching to infinite. For t greater than 0, the circuit undergoes transiences. But as t approaches to infinite, the circuit reaches steady state again. The inductor acts like a short circuit and the capacitor acts like an open circuit. And remember, now what we are going to consider? We are going to consider the circuit number B in steady state. The circuit when we have the switch open, right? So again, inductor acts like a short circuit and capacitor acts like an open circuit, like this and like this. So I of infinite is 0 and V of infinite is 12. All this 12 volts would go and dump in this hole. And what would be the current? Current would be 0. Right? Now, this is your task. After listening to the first part or the first example, you are able to solve this problem. You have to solve this problem and submit your results to me, right? Now let's see another example. In this example, our circuit is little bit changed. This one is our circuit. What we have to find out? IL of 0 positive, VC of 0 positive, VR of 0 positive, DIL of 0 positive, D of VC of 0 positive, IL of infinite, VC of infinite, and VR of infinite, right? Now let's start to solve this question. In first step, for t less than 0. For t less than 0, as we know that this unit step function is 0. Unit step function states that for t less than 0, its value is 0, and for t greater than 0, its value is 1. This is u of t, right? So at t of 0 negative, the circuit has reached a steady state. Inductor can be replaced by short circuit, capacitor can be replaced by open circuit, all the same things as we have discussed previously, and these are practically implemented in this circuit. So IL of 0 negative is 0. VR of 0 negative is again 0. Why? Because no source is connected over here, it is disconnected. VC of 0 negative is what? It is minus 20 volts. Why? Because all this voltage dumped into this open circuit, right? As we already know, what is the rule? If you had a open circuit in your circuit and a voltage source is connected across it, then all the voltage would drop in that open circuit. You have to verify this also in your lab. And similarly, for open circuit, the current would be 0. This is what happening over here. Although the derivative of these quantities at t is equal to 0 negative is not required, it is evident that they are all 0. As the above things are 0, so derivatives are also 0, as we have seen in our previous example. So, thus as the circuit reaches its steady state, nothing is going to change. Now, for t greater than 0, the unit step function, it is going to have a value of 1, right? So the circuit is now equivalent to the 1 in this. Now our source, this current source is connected. Why? Because in u of t, we are going to have the value for t greater than 0 and t equal to 0, not t less than 0. Now this is our circuit. Since the inductor current and capacitor voltage cannot change abruptly, same situation. So I of L of 0 is equal to I of L of 0 negative is equal to 0. Similarly, V of C of 0 positive is equal to V of C of 0 negative, that is equal to minus 20 volts. Although the voltage across the 4 ohm resistor is not required, we will use it to apply KVL and KCL. So we call it as V naught, this one at 4 ohms. Applying KCL at node A. Now we are going to apply nodal analysis. We are going to form the equations. So what would be? 3 is equal to VR of 0 divided by 2 plus V0, this one, divided by 4. If you would solve it by using simple nodal equations, you have to increase a step over here, right? Remember what we would do in simple nodal analysis. Now apply KVL to the middle mesh. Minus V of R of 0 plus V of naught of 0 plus VC positive plus 20 volts is equal to 0. This one, this mesh. Since Vc of 0 positive is equal to minus 20 volts, putting the value in above equation, what we get is Vr of 0 positive is equal to V naught of 0 positive. So from above two equations, from equation number 3 and equation number 5, we got equation number 6, that is Vr of 0 positive is equal to V naught of 0 positive, which is equal to 4 volts. You have to simplify them, right? When you put all these values in these equations, you got Vr, which is equal to V naught of 0, this one at 4 ohm, is equal to 4 volts. Now the part B of our circuit. In the part B, we have to find out L di over derivatives. We have to find out the derivatives. So L di over dt is equal to VL, as we already know that. So d IL over dt is equal to VL of 0 positive over L, the value of given L. After again applying KVL, we got DIL over dt at 0 positive is equal to 0. Similarly, as C dV over dt is equal to IC, again we find out the values and we come across the results that V naught of 0 positive is equal to 4, IL of 0 positive is equal to 0, IC of 0 positive is equal to 1, this one, and putting the values over here, what we got is we got dVc over dt is equal to 2 volts per second, right? Now the final third one, d of VR over dt across resistor. Again, we apply Kirchhoff's current law at node number A, the node we have defined in our previous slide. 3 is equal to VR over 2 plus V out over 4. Now again taking derivatives, this one would be 0 is equal to 2 dVR over dt plus dV naught over dt. We can also apply KVL on the central mesh as we have done previously, like this, again taking their derivatives, and finally what we got dVr over dt is equal to 2 by 3 volts per second. We can also find out dir of 0 positive or over dt as Vr is equal to 5 IR, putting the values, and finally what we got this result. Now the last one, for t approaching to infinite, then the circuit reaches its steady state. As in circuit number A, 3 ampere current source is now in operative state in circuit number A, in first circuit, right? The circuit given in your question. By applying the current deviant principle, we got IL of infinite is equal to 2 over 2 plus 4 multiplied by 3 amperes, which is equal to 1 ampere. And similarly, VR of infinite is equal to 4 over 2 plus 4 into 3 ampere multiplied by 2. This was also given in our previous state, is equal to 4 volts. And Vc of infinite is, again, remember, we got the hole in the circuit, and that would be equal to minus 20 volts. Now you have to solve this problem by keeping in mind the previous example. Now remember one thing, you all have to remember the thing that you can't just listen to the lecture and understand the problem. You have to solve it to get a clear understanding of the problem, right? Thank you.